Just going to verify that it's recording. Recording is in progress, it says. Okay, good. Okay, well, this is data review, plotting and principal components analysis. So always look at your data. It sounds kind of stupid to have to say that, but for a while I actually got in this habit of importing data directly into principal components analysis and not, looking at it to begin with. And so don't be like that. Um, Review your data before you start modeling. This might reveal outliers. It'll maybe suggest to you what pre-processing methods you ought to use. It'll show you what features are important, and hopefully it'll identify any trends that you see. You usually find some things that you weren't expecting if you actually look at it. Plot the raw and the pre-processed data. I really like the color by feature that we have in our software. It's especially useful, and I'm going to show you some examples of that. And then it's also great to plot data that's mean centered, at least, so you can look at deviations from your average data. And then besides that, use principal components analysis. And principal components analysis, of course, is our low dimension window on our high dimensional space. And it's an incredibly useful tool for looking at data. Very good at identifying outliers and showing you trends in the data. So plot your data. We actually got to this point where we got our data into the analysis window. And all you have to do to plot it is just right click or shift click on the X block icon to bring up the plot data and work from there. And so I think at this point, oh yeah, just one more thing. And that'll bring up this plot controls window, and we're going to be using that a lot. So with that, I'm actually going to shift over and work from the software here. So I'm going to minimize that window. I'm going to get rid of this one right here, and I don't need this one anymore. So I'm here. We've gotten our data in to the analysis interface. And let me just give you a little tour here as I get started. The first window that we worked with was the workspace browser. And if you're new to PLS Toolbox and Solo, this is the first window that you see when you open our software. If you're a MATLAB user, you bring this window up by typing the word browse at the command line. We'll bring this up. If you're a Solo user, this is the first window that you're presented with. Instead of saying PLS up here, it'll say Solo though instead. Other than that, it should look exactly the same. In this pane of the workspace browser, we have the different tools that we have available. And those are things like our data set editor, the principal components analysis window, partial least squares. Those are our favorites here. There are other tools available that you can get by clicking on that. Things like the multi-block tool or the model optimizer in here. But for decomposition methods, those are things like principal components analysis that decompose data sets, multivariate curve resolution, Parafac is a data decomposition tool. And then there's the regression methods are listed right here, and that includes of course PLS, but also multiple linear regression, classical least squares, all these nonlinear ones, they're all in here. Tools for classification can be found in here. So this is where all the tools reside. Here's where the data resides. It shows you what data is currently loaded into memory. And then down in here is the model cache. And the model cache actually keeps copies of all of your models that you've been developing along the way. And so those stay available down here. And it captures all the models that you make and provides a record, and they show up here. Here's where the demo data sets are. We're not going to be using any additional demo data here, but we've got a lot of demo data sets that you can use to learn the tools with. Okay. And we then got our data into PLS through using the experiment file reader, just pushed it in there. Most of our methods use this same analysis window, we call it, where you've got your data flow on top that shows here our X, our spectra, and our Y, which is our concentrations, how we pre-process them, and then make them into a model. And then if you want to apply that model to new data sets, you can get predictions out this side. And so this is the uh, basic window that most of our methods are put into. So now if we want to start by plotting the data though, if we just mouse over the X and click on it, it'll bring up a list. And one of the things in the list is plot data. And that's the one I want to do here. And so here now is the first plot that comes up. And you'll notice that I actually got two windows up when I did that. I have my plot controls window and the actual plot. This plot controls window controls what is in the plotting windows right here. And you can have multiple plots up, but you'll only ever have one plot controls window. And here, this first item in it tells you what plot you're controlling. You're controlling figure 1 calibration X block data. And that's this one right here. If you have multiple plot windows up, whichever one you've clicked in last is the one that plot controls will be controlling. Okay, so here's our data. This is the mean Raman spectra of these glucose in water samples. Looks like that. And if we click on data now instead, that will actually show us all of the spectra plotted on top of each other right here. And of course, when you do that, we actually first see something interesting. It looks like I have one stray one right here that I can see in green. We can zoom in on that in up here to the right. You have a zoom tool. If you're using MATLAB, an old version of MATLAB, it might not have that here. It I think used to reside up in here. The zoom tools did. Um, in most modern ones in the last 3 years or 4 years, it's been here. So I'll click on that and I could select the part of it that I want to look at. So here, for instance, I could see some real variation in some of the peaks, especially down here again. It's pretty consistent in quite a few places, though I can see that it looks like we're getting about the same variation in peaks across here. I can zoom back out, go over here, and I can see I've got another feature over on this side that looks like it is also varying with concentration. I also see a few effects of cosmic ray spikes. We have a few of those. Looks like they're present in this data. Okay, zoom back out again. Well, what else can I do here? One of the things that I really like to do is use the color by feature on the data. So I'm going to go over to the plot controls window and choose color by and say load from Y block and say okay. And there's only one thing in the Y block, and that's concentration. And so I'll say okay, do that. And now my spectra is actually colored by concentration. So let me put the legend on here, the color bar, which is this icon right here. And I can see that, I have samples from 5 to 40, I think, milligrams per milliliter. And now when I look at them, I can see how they're ordered by that. So especially let's look at this feature here. So we can really see that they're well grouped, except for this one stray one here. pick a feature like this one here, and we see that they appear to line up by concentration, and that the spectra from the replicate samples all lie pretty much on top of each other uh, there. So you see a little variation in them from sample to sample that are supposed to be the same, but they all pretty much lie on top of each other. So that's good. That looks like a good start here. Alrighty. A couple more things I like to point out here. Okay, let's go back. There we go. It's also nice to just plot, as we did, we showed before the mean spectrum. Oh, now that's going to be the mean of each group. So let me undo my coloring just a second. None. Okay, there we go. Bingo. Okay, so there's my mean spectrum. It's also nice to show the standard deviation spectra. That shows you where you're getting variation here. And you can also do the mean plus the standard deviation. And that's a little hard to see here. Um, but really, when you do the standard deviation, that really shows you where you're getting your variation in this data set. So you're not actually getting that much in the low wave numbers here, and there's a big region here where there's not much going on as well. So it looks like maybe you would not want to use this region, and that region in here. There's doesn't appear to be really much useful going on in there. And still, we've also noted that we have this one stray sample, which we expect that'll show up here as we go along. Okay. I think that was all I wanted to do on that. So let me go back to the presentation. Oh, there was one more thing, in fact, that I did want to do there. So I'm going to close this window. Uh, One of the things that's nice to do is to mean center your data, and that is subtract the average sample from every sample and just look at the deviations from that. And here, if I've set my pre-processing, I can click pre-processing and change this to mean center right there. And then I go back to this P for pre-processing and say plot pre-processed data. This will actually show me my data that's been pre-processed. And so now you've subtracted the average sample off of this, and now this is what your data looks like. And this really brings the variations to light here. Now we can use color by on this as well. And I'll do that load from the Y block. And bingo, there we go. Put the legend back on. And so you see again that most things line up pretty well. Um, Also, we see our one sample here that is kind of a stray. And I always forget the command to identify curve. Do you remember that one, Scott? There, there it
Right
is.
click, yeah.
Yeah, it's sample number 5. Um, so uh, that one, for instance, we'll probably see him crop up again. And he should be down here with these other ones right there. So something's up with that. You also really see the effect of the cosmic ray spikes in here. Mostly I see those in this region where there isn't much going on. Um, and I don't really plan to use that anyhow. Okay.
We had a question about when you apply pre-processing to your X block, do you need to apply it to the Y
Hmm.
or mean center the Y specifically in this example?
Uh, yeah. Of course, now I'm not making a regression model yet, but in fact, if generally with pre-processing, if you mean center your spectra, you should also mean center your concentration values. And in some instances, and you might build a model without mean centering the X, and in that case, you would also not mean center the Y. Most models are built with mean centering, and you then have mean centering as the last pre-processing step for both spectra and for concentrations. Okay, that's about all I really wanted to look at. So let's see, I did that. And here's a bunch of plotting and visualization resources. We've done a number of webinars, everything you need to know about data visualization with PLS Toolbox and Solo, everything you need to know about making great plots in PLS Toolbox and Solo, um, everything you need to know about Trend Tool for exploring ordered data. That's another plotting tool that's useful for doing things like integrating peak areas and things like that. And then we have a class at our Eigenvector University, data visualization from simple plots to UMAP, and we'll be presenting that again in May in Seattle. Will be part of the agenda there. Okay, so let's move on and do a little principal components analysis. So why PCA? Well, principal components is the most important tool in chemometrics and probably data science in general, and it is ubiquitous. Uh, Principal components reduces the number of dimensions in a data set while retaining the maximum amount of information, that is variance, possible. It makes it easy to see the structure in your data, how your data clusters, what outliers you have. It's interpretable. You can look at the model loadings to tell you how your spectra is changing to produce the variations that you see in your samples. Um, it's tremendously useful for data exploration, visualization, screening, data compression. It's part of an awful lot of other methods. So our PCA nomenclature and conventions, we take our data and arrange it in matrices where rows correspond to samples or observations. In our case, spectra, the spectra are in the rows, and columns correspond to variables. So the uh, wavelengths are in the columns. Uh, Notation, we use M as the number of samples or observations, N as number of variables, K as number of principal components, and we'll have these things called scores and loadings, P's and T's, T's and P's. Well, usually before we do a PCA model, we do something like mean centering. We do some pre-processing to the data. And the reason is that principal components is scale dependent. Numerically larger variables will appear more important in PCA models. So often, or really usually, we're most interested in how the data varies around its mean. So mean centering is done by just subtracting the mean off of each column, thus forming a matrix where each column has a mean of 0. And you can just think of this in our example as we have the mean spectrum, which we plotted the average spectrum. You just subtract the average spectrum from every spectrum. That's mean centering. But even at that, in some instances, you might want to do variance scaling. PCA is scale dependent. Variation is associated with importance. This may or may not be true. In the system that we're looking at, it probably is, because really it's the features that are changing the most, that have the most variation here, that are really where the chemistry is going on in this little example data set. I mean, those are really related to the changes in glucose concentration. So uh, for us, variance probably is associated with importance. Um, if your variables have different units, then you usually can't say that. That's like if you have a set of engineering variables where you've got temperatures, pressures, concentrations all in one matrix. When they're in different units, then you can't really say that variance is proportional to importance. Uh, Auto scaling is where you divide each mean-centered variable by its standard deviation. The result is variables with unit variance. And auto scaling really means that you've done both mean centering and scaling to unit variance. There are other scalings that you might want to use, such as noise level in the variables. In other techniques, such as mass spec, you might want to use Poisson scaling. So there are other variations. Here, though, we're really just going to stick with mean centering because we do want to emphasize where we see the most variation in the data.
Hey Barry, we had just a few follow-ons there, and um, spe especially with how you determine whether you're going to apply your preprocessing to the Y block.
Mm-hmm.
So for example, like if you're using auto scaling, do you want to auto scale both X and Y? Um, and then with mean centering, um, we had a user say, well, they've been shown that you mean center the X, but not necessarily the Y if you're using, spectral data.
Um, uh, yeah, okay. So let me back up to the first question. If you only have one Y variable, it doesn't matter if you auto scale it or mean center it. That makes no difference in most modeling methods, except for ones in some nonlinear methods where if the scale's outside of, the plus or minus one range, it doesn't like it. But for the most part, auto scaling or mean centering a single Y variable is basically the same. PLS model doesn't care at all. What it cares about is that it's mean centered or not. And auto scaling includes mean centering. As far as making models that where X is mean centered and Y is not, I'd invite you to think about that one. Because what does that mean? Well, if you've mean centered X, your spectra that's zero is the one that's the average once you've mean centered. And if you haven't mean centered Y, then your Y that's zero is the, one the lowest concentration. And so you're trying to match a zero with something that where zero is the mean average thing to oh God, I'm not explaining this very well. Anyhow, I just invite you to think about the geometry of that because the once you've mean centered, the average spectra is going to sort of predict a zero. So that's not the one you want to match up with your Y if it's not mean centered. Okay. Very few instances I've ever seen where that works. So, and that's one of the things that you'll make a mistake and do it that way, and you'll go, "Oh God, what's going on?" So that's not usual. Okay, anything else?
No, no, and I'll say like, at the help desk, when people approach us with unusual results, we that's the first thing we look at is what's going on with preprocessing.
Yeah. Thanks, Scott. Okay. So principal components analysis. Here's the basic idea. This is a diagram we have drawn for just a simple system here with three variables. So I've got variable one, variable two, and variable three. And I've got some data points out here in these three dimensions. And this is intentionally drawn to look like these samples are largely all on one plane. So if you made a PCA model of those, the first thing that you do is generally find the mean of that data set. So that's the center of it here. And then the first principal component is a vector that describes the direction of greatest variation in this data set. And that would be along the semi-major axis of this ellipse right here. And so this would be my first principal component. And the second principal component is the direction of second greatest variation in this. and that's that direction. That would be the, I think, called the semi-minor axis of this ellipse. And um, just a couple things. It doesn't really matter if I point this vector the other direction. I could flip these. That's going to just make a sign change in our model down the way. So I can choose this direction or that, this direction or that. I'm choosing these here right now for this example. So that's the basic idea behind a PCA model, is a way to describe your data set. So the math behind that: for a data matrix X with M samples and N variables, generally assumed to be mean-centered and properly scaled, the PCA decomposition is this. We can take our X matrix, which for us is spectra, and decompose it as these scores vectors times loadings vectors. We have pairs of these all the way down to the rank of the data, how many independent variations there are in the data, including the noise. So this number could be pretty high. But we usually stop at some K that's representative of the systematic variation in our system. So here R is the um, rank of the data. It's always less than or equal to the minimum dimension of the data. And these pairs are ordered by the amount of variance captured. Generally, that model is truncated, leaving some small amount of variance in a residual matrix. And so we just go down to K, lump the rest of these into some error matrix right there. We can collect all these T's together and all these P's together and just write it this way. So X equals TK PK transpose plus error. Properties of PCA: the TI and PI are ordered by the amount of variance captured. So the scores form an orthogonal set, which describe relationships between samples. And so, that's really key here, is you're going to get these things called scores, and the scores are going to show you how your samples are ordered in multivariate space. Then the PI, or the loadings, form an orthonormal set, and they describe relationships between variables. And then, so they're going to show you how your variables vary together, the patterns they vary in. K is the number of factors or principal components. And we usually look at scores and loadings plots in pairs. For instance, we look at the scores versus sample numbers and the loadings versus variable number, or we plot them against each other. Um, so scores versus each other and loadings versus each other. So a loading, what is a loading? Well, let's say we have this data set here that's just these green samples. It's already been mean centered. So I've got the center of my plot here, goes through the center of the data. So this direction here would be the best fit line through the data, if you will. And that's my principal components one. And, again, that could have been minus, but here I'll draw it this way. So what's a loading? Well, a loading is just a direction for this. So if this is 1 unit right here, then I would go out 3 units, 1, 2, 3 this way, and up 2, 1, 2, and that would be my loading. 3, 2 would describe the direction of this. Well, I don't like uh, vectors that aren't unit vectors, so I'm going to take that 3, 2 and divide it by the length of this vector, 3 squared plus 2 squared, to get a unit vector, a vector of unit length. So my loading here for this is 0.83 and 0.55. So it points a little more in direction in X1 than it does in X2. Okay, well, what's a score? A score is just how far along in that direction you are. So pick this sample right here. What would its score be? Well, this sample, its original coordinates are 2 1/4 and 1. So if I go over here, this is 1 unit, 1, 2 1/4, and up 1, that's where this sample is. If I take the inner product of that with the loading, I get its score, a 2.43. So what does that mean? This sample is 2.43 units in this direction from the middle of the data. This sample would be a little further, maybe 3 something. Samples right in here have scores very close to 0, and samples down on this side would have negative scores. So this sample right here would have a score of about -2.5. And that's what scores are. Scores are just how far along you are in your new dimensions described by the loadings. We also have a property called the Q residual. Q is a measure of the size of the part of each sample not explained by the model. So every single sample, besides having scores, has a Q value, which is just a scalar. It's the sum of squares deviation from the sample to the model. A small q means that sample's well explained by the model, and a large q means it's not. Residuals are orthogonal to the model space. So for those of you who know a little linear algebra, residuals are in the null space of the principal components in the model. And another tool we use all the time is Hotelling's t-squared. So t-squared is the distance of the projection of the sample into the model subspace, so onto the principal components of the model, to the model origin. So again, every sample has one t-squared value. It's the sum of squares of all the scores for a sample that have been weighted to weight them all equally. It's a distance from the origin of the model to the projection of the sample into the model. So a small t-squared means that that sample is close to the center of the data. That's assuming it didn't have a large q value. And a large t-squared means that sample is far from the center of the data. So that's easier to describe really with a picture. So here's our data again in our PCA model. So here's a sample that would have a high q value. That's because it's a long ways off the plane formed by the model here. So if I project it down on here, it winds up here. It's a long distance off. This is a sample with a high t-squared. So it's in the plane of the data, but it's a long ways from the center. So it would have a high score on PC1. It would also have a high negative score on PC2 because it's out this direction a fair ways. So this sample here has a high t-squared. Okay, well, let's do a little PCA of the glucose data. So there's our interface right there, and we're going to then switch. We were in PLS mode, so we're going to switch it to PCA mode by choosing that from the decomposition menu. And let me, okay, come on. Let me go back to the software and do just a little PCA here. I guess I had a feeling that this would run sort of long. That always happens when you have questions. So,
Yeah, we're
yeah,
getting close to 90 minutes here.
yeah, okay. So, all right, we're loaded up, but I'm going to switch the analysis here, go down to decomposition and choose PCA. And I want to make sure that I've got mean centering turned on here. So if I just double check, I'm going to mean center this. So that's good. You can always mouse over it and see what you got. I'm also going to turn my cross validation off. So this check mark here, I'm going to click cross validation and just switch it to none and not worry about that now. We're going to worry about that tomorrow. And I'll say okay. And let's go ahead and get a model. And to get a model, I just click the big green button right here. And the first thing that I'm presented with is a variance captured table right here. And I see that I actually get 95% of the variance is captured in the first principal component. So that sounds good to me that most of the variation is in one direction. I've got a little other variation in some other directions here. So my model chose that it wanted me to look at the first three. I think that's fine to start. So now let's go ahead and do that. And if your model isn't set to 3 here, you can change that by double clicking on the line. So I just double clicked this and set it to 4. And so now this is set to a 4 PC model. I'm going to stick with a 3 for a moment. So I'll double click it, set it back to 3 right there. And let's look at the scores in this model. And to look at the scores in the model, what I do is I clicked on the Erlenmeyer flask here. That brings up the scores plots. So I clicked on that and that brought up a couple of plots here. So this is the window that you're presented with when you first start here. That are kind of all the things that you ought to look at. And the first one is a Q versus T squared plot. And I see in particular, I've got a real stray sample here in my T squared. Most of the sample should be in the lower left-hand corner here. These are the 95% limit lines. Okay, and here's my scores on principal component 2 versus 1. So I see an interesting sample right here. And let's go ahead and select that sample. Here I actually see how the scores on PC1 are ordered with my data set as I brought it in. And probably no surprise that we brought it in as the concentrations got higher. But what I'm going to do now is let's just look at my scores plot. So I just want to look at the scores for the moment. I'm going to double click in this. If I double click on that plot, it'll bring it up by itself right there. And uh, now my first question is what's this sample? You probably already know the answer to that, but I'm going to select it and right there, and I'm going to put the numbers on it by doing that. And uh, oh, that's 19. Okay. Um, why was I thinking it would be a different one than that? Um, so here's our sample 19. God, really? Oh, yeah, it's in the first group. Oh, okay, it's 5. It wasn't sample 5. It was a 5 milligram per milliliter sample that we had shown first. So this belongs in this first group here, only it's actually out there. And so one of the things that you'll find though in a PCA model is that a single sample like this can greatly affect the whole model. So I already know now that this one's pretty interesting. And if I look at the data for that one, it's the one that's offset from the rest of them. And in the interest of time, I'm not going to go through that step there. But we kind of already know what that one is. So let's actually exclude that from the model here. And so I'm going to say in my plot controls, I've selected this sample. I'm going to say exclude that selection. And this gives me a tip that shows me how to put things back in once I've excluded them. I'll say, okay, so I'm going to take that sample out. And now I need to rebuild the model. So if I go back over here to the PCA window, you see the model disappeared. Well, that's because I changed the data. So now I'm going to click on the model button and model again. And um, now it's actually telling me that I might include more components in this. Uh, that's fine. I'm really only going to look at the first 3 here, so I'm going to leave it that way. But I see something interesting here is that my samples appear to group in these groups. I'm going to turn the numbers off. And sort of curious as to why that is. So something that we might do here is color these samples by the Y values. So here then in the plot controls window, I'm going to do color by, and I'm going to load from Y block right here and say, okay, it's the concentration, okay. And now I see that these are the groups, the of samples at the different concentrations. So a couple of things here. I think I'll just turn that off, the confidence limits line there, and put the legend on. So I see a couple of things here that are good. One is that as I go left to right, I go to higher concentrations. On the other hand, as I go up and down, then I see this spread in each of the groups, and they're not all centered there exactly. And so I'm sort of curious as to what causes the spread this way. I know what the left-right is because that's got to be concentration of glucose. And I also have a few kind of strays like that one there, and this one here that are a little more separated from their group. And so that's something that we might want to look at. Um, so a couple of other plots though that we should look at. If I go back to did I already close that window? I think I did. Um, I also want to look at my Q versus T squared. So let's look at the Q versus T squared plot again. So you can see that here I actually have a few samples that have fairly high Q residuals. And let's go ahead and highlight those by selecting them. So, I've got these four right there. And let's go back to my PCA plot again. Scores on PC1 versus scores on PC2. So those are these. And these are ones that, in fact, don't group with their group very much. So it'd be interesting to know what the story with that is. So of course I can look at the loadings from this and learn some things. So here, if I go to the loadings button, that's going to show me what the variation in the spectra is that I'm getting. And so this is right here, the first PC. That just looks like the main variation in the spectra that I know is related to glucose. Now here's the loadings on the second PC. So I seem to be getting this kind of shift in the data, this really low frequency uh, component right here. First off, I know that this first bit of the spectra didn't look very useful here to begin with. So a lot of that is this. And fortunately, this isn't a large amount of the variation. It's a little less than 1%. But I might be able to get rid of part of this variation by just doing a little editing on my spectra to begin with. So I'm going to go back to the first PC and I'm going to get rid of this part, and that part because I don't think those are very interesting anyhow. That doesn't look like that's where there's glucose signal. So I'm going to say first, um, under the edit menu, I'm going to change my selection mode to be X range. Selection mode, X range right there. And now I'm going to do a selection of places that I want to, I'll do it for parts I want to keep. So I click the select. So I want to use this part of the spectrum right there. And I'm going to click select again and hold down my shift key and grab this feature right there. So I've got that part selected. And now I'm going to say edit, include only selection. So that's the only part of the spectrum that I'm going to use right there. And so now that's the part we're using. That means I got to remake the model. So I've left some samples out. I've remade the model. And now let's look at what my scores plot looks like. Still have a fair amount of this variation up and down. So it moved a couple of these around, but it didn't totally get rid of it. Even on this model, my uh, high Q samples are still shown as being somewhat different. And I can also look at the residuals on any of those if I wanted to. So look at the pattern in those. In the interest of time here, since we're already way over, I'm not going to do that, but I'm going to point out the things that we've learned by doing PCA in this. We found our one real flyer sample was obvious here. We saw that by eye just by looking at the data, so we kind of expected that. But we've located three other samples that have pretty high Q residuals in this model. And so those are kind of suspect as we move ahead here. And so those still show as being really unique samples even after I've done a little wavelength selection here in this data. We might even picked up another one. Uh, so I know I've got those to watch out for. I do know, though, that just one more point here, Scott, that my main variation seems to be related to concentration, and that's good news. Yeah, Scott.
The question was, are these pure solutions of glucose?
And water. I believe so.
And so, yeah, you're describing almost all of the variation in one PC.
Right. The funny thing is though it's still not all of it. Uh, which is that, it looks like a real simple system with only one thing varying, but in fact, there's at least a couple of other minor things that are going on, and that will show up when we go to make our regression model out of this. We will
And then,
find out that we won't have a rank one regression model on this for an optimal model.
as far as like uh, outliers and excluding them, like, is there any guidelines for that?
Yeah, there definitely is. The first thing is what we would prefer to do is find out why these samples are wrong. Why did that one have the baseline in it? What's contributing to the variation that we see uh, in the up down in this plot? Why did they smear out? And I don't have a good answer to that because I didn't take this data set and I don't have access right now to the people that did. But those are really good questions to answer as you go along. Certainly, any sample that's a blunder that was measured wrong, because the sample wasn't presented correctly or whatever, you can throw that out. Okay, anything that's wrong. The real question is these ones that are just slightly different, do they represent some variation that you're going to see in the future? Um, if they don't, fine, toss them out. If they do, then you got to think about, well, do I keep them in there in order to help the model learn to ignore them if they're presented with those samples again? Uh, that's the question that you have to answer. So it turns out it's not that simple sometimes to figure out what you can throw out of your data set. And in this data set, though, this model is going to be a whole lot better without those. I would still like to have some explanation as to why they were different. And this is also why you want to look at your data as it comes in, because some of these things then are things that you can check on while you're making measurements. And it's a lot easier to go back and remeasure a sample if you have just done it. So, uh,
There was a question about, could clutter improve the situation? Uh, I'm guessing maybe that's adding variation that you expect to see. Maybe.
well, what we're assuming here is that clutter is always present, and um, but if you mean, do you want to add additional variation due to extraneous sources in order for the model to help learn to deal with them? Well, if you don't think that they exist and about the amounts that they're going to be in the future, maybe that'd be a good idea. Um, uh, we it's good to have good examples of the stuff you want to ignore so you can learn to ignore it. But yeah, that isn't one that happens very often. Okay, well, let's just summarize PCA. You start PCA with data pre-processing. You almost always mean center. Um, Auto scale to balance the variance. We're not doing that here. There are a lot of other methods available to reduce nuisance variance, like multiplicative scatter correction. I have just a few words to say about those tomorrow. Uh, PCA extracts scores and loadings in pairs, starting with the greatest variation. Scores show you relationships between your samples. Loadings show you relationships between your variables, and together they show how your variables combine to create the trends that you see in the samples. Additional diagnostics of Q and T squared, and those are important. And here's some PCA resources from our webinar series, everything you need to know about how to do principal components analysis. If you want to be able to read the equations for PCA and PLS and et cetera, Neil and I long ago wrote this Introduction to Linear Algebra, which contains all the linear algebra you need to follow most chemometric methods. And that's available actually on our website. There's a really good paper by Rasmus Bro and August Schmilde on principal components analysis that they did in 2014. So I recognize going out and finding that. And no surprise, we have an Eigenvector University class and also one of our online recorded classes on both linear algebra and principal components analysis, and those are available as well. And I think that wraps it up for the day. What else we got, Scott?
We're pretty quiet right now. We'll give it another minute or two, or if people have questions they want to post in the chat.
Okay.
Yeah, I'll say that I got a couple of good questions, sort of privately, and I'd just say that you know, don't you don't need to text me or chat me privately. These are all really good questions, and I try to get them out there for people to hear.
Yeah, if you have them, somebody else probably does too. Okay, well, I think that then closes us out for the day. Just 15 plus minutes late. And thanks everybody for being here today. And tomorrow we'll start with a little bit of partial least squares and go on from there.
Yeah, I think someone earlier in the chat asked about the link for tomorrow, and they hadn't received it.
Yep, I
Um,
didn't send that out yet purposely so you wouldn't get confused about which one was which. So we'll send that
like
out.
I did this morning.
Yeah, we'll send that out this afternoon, along with a copy of the notes for the second half of the class once we finish them. So still have a few slides to add in that, and we'll get them out to you. Okay, thanks. I'm turning the recording off.
Alrighty.